In our last page, we're doing the same thing. They've given us the graphs, all except for one. And this is the set of directions that you would see if you knew both with respect to x and with respect to y. So in example 4, it says, given that y is equal to the natural log of x and y is equal to x minus 2, we want to find the area of the shaded region here by integrating with respect to x. And it says use your calculator, so that's good news. So the first thing that we want to do is actually take a look at this graph and identify which one of these is the natural log of x and which one is x minus 2. So you won't always be told. Hopefully you can see that the linear function here is y is equal to x minus 2, and then here this curve is y is equal to the natural log of x. So what we're going to do is actually go in, since we're going to use our calculator, and put these in. This is just for my notation, putting this in y sub 1 and this in y sub 2 so that I remember. You've got the natural log of x here, and then you've got x minus 2. So all I did was just put these in my calculator, and then I just went into the home screen. So one thing that I do need here is that I need to determine which is the top and which is the bottom. And clearly, I hope you can see that your natural log of x is your top. So I'm just going to make an indication here. This is my top, this is my bottom. So now the only thing I need are my limits from a to b. So if I call this a and this b, I'm going to say that a is equal to, b is equal to. So I'm going to graph. These are in here, and I'm actually just going to see what happens. I do need to change my window though because I have some negatives. So let's go here. Our minimum, let's make it, I don't know, -2 to, let's say, 1. And let's see what happens when I graph. Okay, there's my natural log. I don't think I'm going to get what I need though. Nope. I need to extend this here, so that means I need to extend my x. I don't know, let's make that 5 graph and see what we get. Oop. Okay, so that means now I also need to extend my y. So when I extend my y window, let's take it up to 3 graph. And again, this is just playing with the graph, so you don't know until you get there, and that's perfect. Okay, so we're looking for our point of intersection here, A, and our point of intersection here, B. So we're going to calculate the point of intersection, and I'm actually going to get close over here. Press enter. It jumped to the second one. I'm close enough to it. So this is 0.1585. And then I'll calculate this point of intersection so I can get myself set up. Let me get closer to the other one. Okay, so I'm going to press enter, enter, enter. 3.1461. 3.1461. Okay, so you can do this one of two ways. You have designated what a and b are equal to, so when you write your integral, you can identify that. But if you have minimal space, my recommendation is write in your bounds. You have them. This is 0.1585 to 3.1461, and we have our top function, which is the natural log of x, minus the bottom function of x minus 2 dx. Now, once you have the setup written down, you don't have to do anything but go into your home screen. Okay, and we've got the integral from 0.1585 to 3.1461. Then we've got y sub 1 minus y sub 2 with respect to x. And there's your area between the two curves, 1.949. Okay, so most likely we'll be looking for both the setup, bounds, answer. Okay, so what you guys are going to do is work on example 5, and then I will go through and show you the answer, and this is what you would need to check. Okay, so since here we're only looking for region S, we're not looking for region R, we're actually going to do that in the next lesson. You can clearly see that you have a top and you have a bottom. If you were to accidentally try to find region R, in this case we do not have a clear top and bottom, we have a right and a left. This would be with respect to Y, which is what we'll discuss next class. So your region here, if you have top minus bottom, you're going to go from left to right. This is your left bound of 0. Your right bound, you had to find that point of intersection, was 0.9021. You had to indicate what your top function was and what your bottom function was. So here we had the cubic, here we had the trig, and there's your area. In the second to the last example here, this would be an example of what you might see on an FRQ, or maybe a multiple choice, but it says find a vertical line where x is equal to k that would divide the area enclosed by this given region of x is equal to the square root of y, x is equal to 2, and y is equal to 0 into 2 equal parts. So this is actually with respect to x because we want a vertical line. Okay, we need to know what x is equal to. So we would need to know, first of all, what that would be. So I don't know if this is cutting it directly in half, so I'm just going to put an imaginary vertical line down here, and it's not at that exact point. Okay, so first of all, if I want it in 2 equal halves, I don't know what this exact value is, so this is what we want to find. So we want to know what is this value for x where this green region right here, that area under the curve, is going to be equal to this area right here. Okay? So we want these two equal to each other, meaning we want to go from 0 to who knows, and from who knows to this value right here, which is 2, and set these two equal to each other. So we need to set up 2 integrals in order to figure this out. In order, first of all, you didn't have this graph, so in order to get this graph, I actually had to sketch this. So what I did was I realized they only wanted the positive version, so I solved this for y so that I could actually sketch it, and then I only took the positive side. Because this is a parabola that has 2 sides, but because they only gave me the positive, I only wanted the positive side. So then what we do is we're going to leave this just like this, and this is our function, okay? And it's technically top minus bottom, and this bottom, because this is our bound, is where y is equal to 0, which is what this is. So when we have x squared minus 0, it's just x squared. So what we're saying is from 0 to some unknown value, the area under the curve from 0 to k of x squared, and I'll write it like this first, minus 0, which is top minus bottom, dx, needs to be equal to the area under the curve from k to 2 of x squared minus 0 dx. Now again, that's going to go away, but I just wanted you to understand it's still top minus bottom. So when we integrate technically x squared, this is 1/3 x cubed to be evaluated from 0 to k, and that should be equal to 1/3 x cubed from k to 2. So in this case, since this 1/3 is just a coefficient, you have one on this side and one on this side, they would cancel each other out, and now we can evaluate. You want to go f of b minus f of a, so this is k cubed minus 0 cubed, and that's equal to 2 cubed minus k cubed. So I'm actually going to take this up here. So k cubed is equal to 8 minus k cubed. This is now just an equation. Add k cubed over here, so you have 2k cubed is equal to 8. Divide by 2. Take the cubed root. So k is equal to the cube root of 4, which if I go into my calculator and I take the cube root of 4, I get 1.587. So we would think that 1 would be dead smack in the middle, but in order for these two areas to be equal, based on the curve, it has to be at about 1.6 for those two areas to be equal. So this is how you would solve for a vertical line that would cut the region in half. This last example here is an application, and it says the accompanying figure shows the acceleration versus time for two cars that move along a straight track. Accelerating from rest, meaning A is equal to 0, at the starting line. What does the area between the two curves over this interval represent? And we have to justify our answer. So first of all, if I find the area between the two curves, I'm integrating acceleration, which in this case would give me velocity. So what we have here is car number 2, and we have car number 1. Okay? This is my lower bound, which is 0, the starting line, and t is my upper bound. So if we integrate the area under the curve, which is the acceleration, this is actually going to give us the velocity. So the area between the two curves represents the difference in the velocity of the two cars from start time to time t.